Now we'll shift our gears and we'll discuss about random variables. So I discussed a lot of probability so far. We initially went to what probability is, then we saw counting, we saw prerequisites of probability, then we went to conditional probability. Now this random variable, if you see this topic, there are two things like this. When I first saw these words, this is random and variable. Like it didn't make sense to me. Like variable, what is something is varying, and what is random, something is varying at random. Okay, so even when the topic is taught, the definition are too tedious. If you look at Wikipedia will say you like random variable as it goes through the measures or something. So if you know measure theory, if you know information theory, then only you understand these definitions. So first, let's see an intuitive way of explaining these things, and after that, we'll go into mathematical formalities. Okay? So what is a random variable? So if you conduct an experiment, so now the experiment is associated with randomness. That is the assumption that we have. The experiment is associated with random. That's why we are learning probability. So now, once we perform these experiments, sometimes we are not interested in the outcome itself. We are not interested in the actual outcome. So rather, we are interested in some function of outcome. Okay, we are interested in some function of outcome. Interested in some function of outcome. So what's the meaning of that? Let's suppose if you roll a die. Okay, if you roll two dice, you are not interested in what is the total outcome. So we also can have that sample space. Let's suppose 1,1, 1,2, and so on till 6,6. This is one possibility. You can list all the outcomes possible, but many other times you have seen, even when we discuss these problems, so we were interested in the sum is 7. Okay, when we roll two dice, what is the probability that both the faces have, when we sum them together, the sum is 7 or sum is 8 or something like that. So we are interested in some function of these outcomes. Okay, that's where the random variables come into picture. Okay, so this is one of the intuitive explanations that you can think. So we are not interested in exact outcomes, but something that has to do with the outcome, some function of these outcomes. So now we can think it like this. So we have a function. Okay, what is function? We have had a good I think 4 or 5 lectures on these where we sort of try to develop the understanding of what functions is. So they take an input and you have an output over here. So now if I am having a class of students, so let's suppose I have students here over here. So we have a set of students. Let's say we'll write it like this. Student over here is Mahmood, let's say Muzaffar, something of this, or Arshan, and let's say Anwar Saab. I'll write these students over here. So if you see, if I now sample these students at random, so my experiment is consider this as a set, and I'll randomly sample one of the students. Let's suppose what I'll do is, once I sample this, I have a black box that is a function to me. Let's suppose this is a measuring balance. It it somehow gives me the weight of a person. So if I let's suppose give Mahmood, so it will give me the weight of Mahmood. Let's suppose weight is 70 kg, something of this sort. So again, if I give some other thing to it, if I give Muzaffar, let's suppose weight of Muzaffar, let's suppose is 82 kg, something of this sort. Okay, now you see this, there is an experiment. So experiment has some randomness associated. What is the randomness? That I am sampling these students at random. Then I am giving that as an input to some function, to some black box over here. That black box here is I am measuring their weight. I have a weight machine. Okay, that can be thought as a function. Then I am getting an output. So I am giving some input and I am getting some output over here. Similarly, I can have some other function also. I can measure their height. Okay, this was weight. I can measure their height. So now I'll give input as let's suppose Mahmood. So height, I think in meters, let's suppose 1.7 meters. Similarly, if I give Muzaffar, 1.8 meters, something of this sort. So now you saw that initially the experiment was, this was our experiment. The experiment has some randomness associated. What's the randomness? That whenever I sample students, I sample them at random. I just pick up a student based on some criteria. I picked up Mahmood, I picked up Muzaffar, and then the second step of the experiment was I was assigning that input to some function. Okay, that function was a black box to us which performed something on that. So here weight, measuring of a weight, it can be thought as a function, and measuring of height can be thought of a function. It takes an input, gives an output. So Muzaffar and Mahmoud were given to this weight function and give answers to 70 and 80. So again, if you give Mahmoud and Muzaffar to this function height, so it will give 1.7 meter and 1.8 meter. So this is how you can think of random variables. So both of these things are random variables. So this weight over here is a random variable. This height over here is a random variable. Okay. So now what is a random variable? So random variable is a function. So random variable is a function. And then what this function does, it takes the sample space. It takes the sample space. Takes sample space and assigns them a real value. So now you take a sample space. Let's suppose after that, once you sample a thing and then you pass it through a function, that function assigns it some real number. Okay. And why is this important? Because I told you that sometimes we are not interested in the exact outcomes, but rather what is in some aspect of the experiment. So one more example that I'll give over here is, let's suppose you have 2 coins, or let's suppose you have 4 coins. If you have 4 coins, and if you want to enumerate all the outcomes of this experiment, so you can start with head, and keep on changing all these things and come to tail. So total number of possible outcomes are 2 to the power 4. 16 outcomes are possible. Now, if I am not interested in the outcomes, so sometimes, many of the times we have seen this, that probability of 2 heads among these 4 heads. So this can be the question. So now I can introduce a random variable here. I can say, okay, let this x be a variable which tells me the number of heads we have. Okay, x is number of heads. So x can take values 0, 1, 2, 3, or 4. So now this is a random variable. So I introduce a random variable instead of enumerating all of this output. That's 16. I just enumerate this. I said x is a random variable which tells me the number of heads there are in the four flip of coins. So now I introduce one more random. Let's suppose now if we have, say, 100 flips. So what was the possible number of outcomes total in the sample space? How many elements would be there? 2 to the power 100. That's too huge. Now if you only want to have a discussion on some aspect of the experiment, let's suppose number of tails in the experiment. Okay, so number of tails is the aspect of this experiment. So there can be multiple aspects to an experiment. So if you're interested in one aspect of the experiment, so in that aspect it's not necessary that you will enumerate all the outcome. You will enumerate all the possible outcomes and then you will write them one by one and then make a decision based on that. So it is better to introduce some variable. We're saying that, let's suppose y is a variable which says number of tails in 100 flip of coin. So the possible values are 0 to 100. Either there can be 0 tail, there can be 1 tail, there can be 2 tails, there can be 100 tails. So you can say that this is our random variable. So now I said 2 things. So one thing in random variables is when you want to focus on one aspect of a thing, when you want to focus on one aspect of the experiment. So rather than writing all the outcomes possible, so it is better to introduce a variable and say this is what it describes. Okay, because you just want to focus on that aspect of the experiment, not the whole experiment itself. The second thing what I said is, now this random variable is actually a function. Now you will have to assign values to these things. So number of let's suppose if you have 4 coins, so you have head, tail. So this was our experiment. Now if I say x is a random variable which takes this as input, it will take sample space and assign it a real value. This is the function. So now the values possible for x are 0, 1, 2, 3, 4. So now I'll have to assign values to this. So when I say x is equal to 0, the probability of x is equal to 0, it's written like this. Okay. So when I write capital X, so this means random variable. So if I write x is equal to small x, so this means it takes this value. The random value capital X takes the value small x. This is how I'll represent notation. So a bit about notation you should be clear about. So this is notation. So when I write something like this, probability of x is equal to 0, I should maybe write it a little bit better so that you understand it while you see the recording. So probability of x is equal to 0. So what is the meaning of this? The meaning of this is probability that in the 4 tosses there is no head. Okay, so this x represents number of heads. So this x over here, it represents number of heads. What is the probability that x is equal to 0? The only possible outcome, basically I am saying that you have a sample space. Out of these sample space, something will match this. Something will match the description. So you will just pick up those outcomes. So what is the outcome that has no tails? That is tail, that is head, tail. It has no heads. So there is only one possible outcome in the sample space which has 0 number of heads. That is, this satisfies this. So what is the probability of this? So total outcomes are how many? 16, I think. So from all heads to all tails. Total number of outcomes are 16. So one outcome has the probability, because all of these are equally likely. So one has 1 by 16. So this is 1 by 16. Now if I am saying probability of x is equal to 1. So how should we read it? This basically means probability that in the 4 tosses of the coins there is one head. Okay, so what are the outcomes possible? You go to the sample space then and you will enumerate these things now. You'll say this is one head, this is one head, this is again one head, and this is one head. So what is the probability? 4 by 16. Okay. Accordingly, you will assign all these things. So probability x is equal to I. So it takes some value I. So there is some value of the probability. So there is a real number. So this is what a random variable is. So random variable is a function which takes the outcomes from the sample space or the sample space itself and assigns it some real value. I think we have a question. Yes, go ahead. So now you understood what a random variable is. So again, I'll summarize this random variable. The first thing that we saw is if we want to see some aspect of experiment, so we can look at one aspect of an experiment, we can introduce this random variable. And second thing that is about random variables is that it's a function. The random variable is a function which takes sample space and it maps it to some real number. So now if you see this, so there is a sample space, so we have the sample space S. So once we define some, let's suppose we have this x random variable, it will define some aspect of the experiment. So once this assigns some value, let's suppose it assigns some value I. So if it gets value, we are saying the probability x is equal to I. That means probability the random variable x will take value I. So it will go to the sample space. It will see how many of the outcomes match the description, how many of the outcomes match this thing, and then it will assign the probability. As we did in the case of coin tosses. The sample space was from all heads to all tails, or from all tails to all heads. So that is total 16 possible outcomes were there. So when I defined this x, so I said x is a random variable which defines the number of tails or number of heads. Let's suppose in this case number of heads in 4 coin tosses. So this was defined as number of heads. So now when I said probability of x is equal to 1, so this should be read as probability of having one head in 4 flips. Okay, this is how it should be read. And then what we'll do is, once we have this, so I said you should go to the sample space then and see how many of the outcomes fit this thing. So I went to the sample space, I said okay, how many of the outcomes fit this description, that is x is equal to 1, number of heads is equal to 1 in these 4 flips. Then I said there are 4 possible things there, there are 4 possibilities, and then I'll assign probability to those. Now I know for each of these things the probability is 1 by 16, so this is 4 by 16. Okay, this is the procedure. This is a function. Now how to calculate that function, I showed you that function. So you have to first see, okay, this is the thing that is fitting it, and go to sample space and retrieve the outcomes, and then for these outcomes assign these values. So if you see now, so this is the sample. I was telling you this is sample space. This is giving me sample space, and now this is my real number, and this is the function. So you have the function random variable. So it takes this sample space into the input. So how do we get this sample space? This is not that we get it directly, we get it indirectly. We have a description, we have a specification, we go to the sample space and then take the possible outcomes that fit this specification and then assign this a number based on the probability rules. Okay, so this is how the random variable should be seen. It should be seen as a function which takes some values or some outcomes from sample space or the whole sample space and assigns it some real number. And again, one more thing that that can be done is, let's suppose you can think if you roll a die. So I'll give more examples to make it more concrete. So roll of a die. If you have this dice, so now you know the possible values are 1 to 6. So you can say x is a random variable which says what is so what number came out on the roll of die. So you can say the numbers can be 1, 2, 3, 4, 5, 6. So one more thing can be defined. So we can now define function on function. So you can say, okay, now we'll not just be interested in roll of a die. Let's now square that number. So I'll be interested in, let's suppose, random variable y, that is square of the number that appears in the die. Okay, square of the number that appears on die. Appears on dice. Here, if you see, this is a y, so y over here can be 1 square 1, 2 square is 4, and so on till 36. Again, flipping a coin, I told you that the possible outcomes are, so you can say number of heads, you can say number of tails. Similarly, in the roll of the tossing of coin, so I can introduce more random variable. Is there a head? So if I am tossing, let's suppose n coins, So if there is a head, I can say 0. So I can have a random variable x. It can take value 0 and 1. So 0 over here means that there is a tail or there is a head. So x is a random variable which says is there a head in n flips. Because now you see we are interested in one aspect of this experiment. That's what I said, tossing of n coins. So I'm to a random variable x which is saying is there a head in n flips. If there isn't a head, then we will say 0. If there is no head, so we'll say, let's suppose 1, or vice versa. You can choose 1 to be 1 meaning that head is there, and 0 means head is not there. I think we have a question. Yes. So in here, if you see, we are not learning any new concept. The concepts that we have learned previously in probability, that's what are getting repeated over here. So if you see event, experiment, all of these things are getting repeated. But this random variable, it's a new notion or a new perspective of looking at those things, so that once we solve some problems, so our notion or intuition will make it easy for that. Will make it easy for ourselves to solve those problems. So shortly we'll take some problem. You will see how random variables help us in solving those problems. Okay, so I was giving you the examples where you can think of these by random variables. So let's do some examples in order to make this notion more concrete about random variables. Let's take question 1 for this session. The question goes like this. So there are 3 balls and they are randomly selected. 3 balls are randomly selected without replacement from an urn containing 20 balls numbered from 1 through 20. If we bet that at least one the ball that is drawn from the urn has the number as larger or equal to 17, what is the probability that we win the bet? Let me explain the question. The question is, we have an urn like this. Okay, in urn we have 20 balls. These balls are numbered from 1, 2, 3 till 20. So we have an urn. In urn we have 20 balls, and in the 20 balls are numbered from 1 to 20. 3 balls are drawn out of it. So 3 balls are drawn out of this urn. So now the question becomes, so we want to see, because let's suppose if we have 2, 4 and 8, if these 3 balls are drawn. Now if you see, the highest number is 8. Okay, the question tells us what is the probability that we will get a number, at least one ball or the highest number among these 3 balls should be greater or equal to 17. We have to compute the probability of this. So the question says, what is the probability that the balls drawn has the number as large or larger than 17, that is greater or equal to 70. So once you draw these 3 balls, so one the ball will have the highest number. So what is the probability that at least one ball will have the largest number will be greater or equal to 70? That's the question. And if you have those, if you have that ball which has number greater or equal to 70, that means you will win the bet. For how many of you the question is clear? So here now, while solving the problem, the first thing that we came up with, what is the total number of combinations possible? So we have 20 balls and we have to choose 3 balls. So this is 20 choose 3 is the total number of combinations possible. Now how to solve the problem? The problem that we have to solve is the highest numbered ball or the highest numbered ball over in these 3 balls should be either 17, it should be 18, it should be 19, or it should be 20. Okay, so we have 4 possible scenarios to look into. So now we have 17, 18, 19 and 20. Now the idea Muzaffar gave is, so you take the 17, now that we have to only choose 2 balls. Okay, and then accordingly you add the probability of this with 18 and choose other 2 balls. You choose 19 and take other 2 balls. You take 20 and take other 2 balls. Okay, and this is now we have to sort of formalize this. So as I said, a random variable is not a new concept. It is just a new perspective to look at this. So I'll say that let me define a random variable x. Okay, so this random variable x will define that the highest numbered ball is, let's suppose I. Highest numbered ball. So now this x can take values. This x can take values from 3, 4, 5 till 20. Why 3? Because you have to at least choose 3 balls. The least numbered balls you can choose is 1, 2 and 3. So what is the highest numbered ball here? 3. So you cannot go below than this. That's what I said. This x says the highest numbered ball. You have to give me the highest numbered ball. So that over here will start from 3. So it can be 3, 4, 5, 6. So the favorable condition for us. So x should take either value 17 or 18 or 19 or 20. Okay, what is the probability of x taking 17? What's the probability of this? So probability x will take value 17, that is the highest number ball will be 17. So we'll fix 17 number ball, and then we'll say we have 2 balls left out of 19. 19, choose 2, and what is the total balls over there? 20, choose 3. So this is total number of combinations is 20, choose 3, because you have to choose 3 balls out of 20. So that is the total number. And when you are saying that, we have to choose the 17th number ball. So 17th number ball is 19, choose 3. Accordingly, now let's suppose we have chose this. So probability, we should have rather done it from 20. Let's say we will do it for 20 because this is the highest number ball. Now let's say x is equal to 19. So now we have to choose x is equal to 19. Now the thing is, we have chosen one of these possibilities. So 20, choose 3 is the number of total possibilities. Now once we have this, so we have 18 balls left. 18, choose, let's suppose 2. 18, choose 2, and we'll compute the probabilities accordingly. Accordingly, when you have probability of x is equal to 18, and you will compute the probability accordingly, and then probability x is equal to 17. You will choose the probability accordingly. You will basically, now you are left with, initially you are left with how many balls? You are left with 19 balls, then you are left with 18 balls, then you are left with 17 balls, then you are left with 16 balls, and you will compute the probability. The probability x is equal to 20 comes out to be 0.150. The probability of this comes out to be 0.134, and the probability of this comes out to be 0.119. So 0.119, and the probability of this comes out to be 0.105. Okay. Now the thing is, when somebody tells you what is the probability that you have to come up with x is greater than or equal to 70, this is what the probability has to be computed. So you will sum all of these things. You will sum this, 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 and this. The probability comes out to be 0.508. Okay. Any questions on this question? So now you saw that the two things I want to emphasize here. The first thing is, we are not learning a new concept, rather a new perspective about the same probabilities that they can be thought. And one more thing that I want to emphasize is the probability. It's not necessary that you'll only have one way of solving a problem in probability. There can be multiple ways of solving a probability. Now the thing is, you have to choose a tool, because I'm just adding tools in your toolbox. You have to bring in a tool, and you feel this is very easy to solve the problem this way, so it is better to use it this way. Okay. So here we had the example. We could have also done it 1 minus probability of non-favorable outcomes, and that was pretty easy than this random variable approach. And random variable is not a new concept, rather just a perspective of solving the probability problem in some other way. Now the other question goes like this. So independent trials consist of flipping of coin have probability p. So you are flipping a coin, and the probability p is there that it will come heads. Okay, all the trials are independent, and it is continuously performed, and till a head appears. So we'll only stop if a head appears, or if n flips are done. So let's suppose you have a coin and you want to flip it 20 times. So you will only stop if a head appears, or you will stop if 20 flips are over. That means if n flips are over, you will stop, or within those n flips you should have at least one toss which will land at head, then you will stop. The question goes, if we have this random variable x, which denotes the number of times the coin is flipped. So this x denotes it is a random variable which denotes number of times the coin is flipped. Okay, you will have to give the probability of this. Probability of x is equal to 1. So what's the meaning of this? The meaning is that probability that on the first flip the head will appear. Probability of x is equal to 2. That means the probability that on the first toss you will have a tail, and on the second toss you will have a head. Accordingly, you will have probability till, let's suppose, n. So can you compute these probabilities? How can you compute these? So now if we read these problems, so this over x is a random variable which says that on it the number of flip that head appears on. If x is equal to 1, this means that the head appeared on the first flip. X is equal to 2 means that head appeared on the second flip. So what's the probability of this? So the probability is that on the first flip we got head. Okay, in here, so we have the flip appeared on the second head. The head appeared on the second flip. So we have first tail and then followed by head. In 3 we have tail followed by head. So how to compute the probability over here? The probability of this is p. The probability of this is 1 minus p multiplied by p. The probability of this is 1 minus p to the power 2 multiplied by p, and so on. In the last case, it becomes interesting. The last case is this, because we are saying that probability that head appears on nth flip, so we have to stop it. That means we can stop it in two ways. Either all of these should be tails, so we'll stop it. Okay, that's x will take n value, so we'll stop the game. Or we'll have this tail, and at the end we'll have this head. This is the this is one of the possibility that we have here. So now if you compute the probability of this in both the cases, and the probability will come out to be 1 by p and to the power n minus 1. Now if we check, so if we check what is the probability of this, probability of union of I goes from 1 to n, x is equal to n. If we check the probability of this, I goes x is equal to I. If we check the probability of this, basically I am asking you to sum all these probabilities. I am asking you to sum probability of x is equal to 1, probability x is equal to 2. So you will see that this probability comes out to be 1. This is again a homework for you, so that you solve the algebra. It won't be difficult. So you will see that the probability comes out to be 1. So the point here is that if you sum up the probabilities of this random variables, it will again be a probability distribution. So it will abide by the axioms of probability. So you will also see that axioms of probability are followed. Probability are followed. So far what you saw, we saw a generic discussion on what random variable is, how can it be seen as a function which takes some input and maps it to some real numbers. Now you saw different different of these examples in the random variable. So now you can see that two things that were persistent in there. The first thing was let's suppose a roll of dice. In that the random variable was x, and it was taking values from 1, 2 till 6. Similarly, in the flips of coin, which is a number of heads, so there you saw the value it was taking was 0, 1, 2, 3, 4, where we had a coin, it was flipped 4 times, and we were saying what is the number of heads in 4 flips of the coin. And then we also saw height of people, weight of people, that was taking x is equal to x values were from, let's suppose 0, make a realistic value, 20 to 200 kilograms. This was weight. And then we had x when it was height of people, so let's suppose a realistic value should be 0.3 meters to, let's say, 2 meters, something of this sort. So now you see two types of these things. The one thing you can see, you have discrete values. You have these discrete values over there. Or one thing that can be continuous values, 200, 201, 20.1, 20.01. So now based on these, we can have two types of random variables. So one is called as discrete random variables, and one is called as continuous random variables. So what is discrete random variable? So in discrete random variable, a random variable can take either finite values, they can take finite values, or countably infinite, or countably infinite. This is discrete. So in continuous, you have uncountably infinite values, or you cannot count them. So what is this countably infinite? So if you see, I'll just have a brief discussion on infinity. So this infinity is not a number. Okay, it is not a number. It's a concept. Okay, books are written on infinity. I'll just give briefly so as to justify what is this uncountably infinite. So infinity is not a number, it's a concept. As perfection is a concept, perfection is not achieved rather. So perfection is what you tend to. So infinity basically is not a number, so it is a concept which defines something which is of humongous scale, okay, which is of huge scale. Now there are different types of infinity. Some infinities are bigger than other infinities. Okay, so how can one infinity be bigger than other infinities? So there's a lot of discussion in that. So I'll tell you what is uncountably infinite and what is countably infinite. So if let's suppose I'll say there is a thing which I have to count. So in counting, if you are counting something, if you can put that counting into one-to-one mapping, if you can put to one-to-one mapping with natural numbers, suppose you found some pattern. So in that pattern, you are saying that okay, I have something to count, and I can put a one-to-one mapping of these things with. If let's suppose you are counting humans in the world, let's say something of this sort. So if you can number them somehow, humans in the world. This is a separate topic on itself, but I'm just wrapping it up so just to give you an idea. So there are different types of infinity. So humans in the world. So if I can put one-to-one mapping with the numbers, I'll say I'll assign 1 to this human 1. I'll have humans. I'll start from 1 and I'll end to this. So you will see that even if this thing is infinite, but if I can put one-to-one mapping of these things by finding some pattern into real numbers. So then I'll call this as countably infinite. Why countably? Because I can put the mapping. But there are some infinities, there are some infinite values. So, but where you cannot have this mapping. So how to put this mapping? You have to find some pattern to map these things. Okay. So where you can find this pattern, where you can have one thing that under consider which you are counting, and you can map it to the real number. You can map it to the natural numbers, and then you will say that we have a mapping from this infinity to the set of other infinities. So this means I have a countable infinity with me. Okay, this still is infinite. It still is a very huge number. There still are huge quantities in here, but I can at least put one-to-one mapping of one quantity. So or maybe I'll write quantity over here. So quantity 1 or entity 1, I can have one-to-one mapping with this natural numbers. So then I'll call this as countably. That's why I'm saying countably infinite. So why countably? Because I can put mapping. Then second thing is where you have uncountably infinite, where you cannot find a pattern to put the mappings. Okay, so I'll just leave the discussion here. There's a lot to say in here, but we'll have a discussion on discrete random variables. Discrete random variables. So again, discrete random variables are the random variables. They can take either finite value, or they can take uncountably infinite values. Okay, I gave you the example, dice rolls. Let's suppose dice roll. If you have that is discrete random variable. So if you have a number of heads in 4 flip of coins, so that is again a discrete random variable, because you are taking a discrete value in there. Is it clear for discrete random variables? For discrete random variables, we define this function. Let's suppose now we have this x is equal to, it can take value a, comma b, comma c, comma d. Let's make it a generic, more generic. So x can take any value from a, b, c, and d. Now we can write it like this: probability of x is equal to a, probability of x is equal to b, probability of x is equal to c, probability of x is equal to d. So we can give all the values to the probabilities, and you know that summation should be equal to 1. So probability of union of all of these, union of all x's. Okay, where x is taking value, let's suppose from this value. So I am taking x's, I'll write this should be equal to 1. Okay, so this thing over here, this function over here is called as probability distribution, or probability mass function. In this case is called as probability mass function, PMF. Why? And this is called as probability distribution. We'll formally define distribution in the subsequent session, but here you can see this. How do you distribute this mass? Now I told you probability can be thought as area or mass. So here you have this one, consider this 1 unit of mass or 1 unit of area. So how do you distribute it? How do you distribute to this? So there are these four possible cases. So how do you distribute it? So if I make a graph like this, so this is, let's suppose A, this is B, this is C, and this is D. So how do I distribute this? Let's suppose A, out of this 1 unit, I'll give this much to A. Out of B, out of this 1 unit, I'll give this much to B. I'll give this much to C. I'll give this much to D. So this over here is called as distribution. So how do we assign the distribution? Is by using this probability mass function. This is called as PMF, or probability mass function of discrete random variable. So for discrete random variables, we have defined one more function that's called as probability mass function. So what it does is it will show you the distribution of these. So if you give it any input, it will show you how much probability is there. Okay, so let's take this example that we earlier did, I think, for the cases of I think head and tail. So we can also come up with a probability mass function there. Okay, so we'll see if, let's suppose we have two outcome possible, x is equal to 0 or 1. Okay, so if we'll say a probability of x is equal to 0 is equal to something, and probability of x is equal to 1 is something. Let's consider this as 1 by 3. Let's have this as 2 by 3. Okay, now you can clearly see that if I sum these up, this comes out to be 1. So this over here is defined as probability. This is a function over here. So this over here is function. So it will define this 1 by 3 and 2 by 3 for this 0 and 1 respectively. So if you have to plot it, so you'll plot it like this. So this is my probability 0 and this is my probability 1. Let's suppose this is 1 by 3 and this is twice this. So this is 2 by 3. 2 by 3 and this is 1 by 3. So this I'll call as probability mass function of this. So accordingly, whatever examples we did so far, you can just compute the probability and you can come up with their probability mass function. Now let's see very important thing. So you understood what a discrete random variable is. So as set with a discrete random variable, so we have this probability function which is called as probability mass function. The concept here over here is that you have this mass, you have this area which is to be distributed. So you distribute it to the outcome. So here the possible outcomes were let's suppose A, B, C, and D, and you accordingly distribute it. So you can get, let's suppose A1 dash or A1, A2, A3, A4, something of this sort. Okay, and then you will plot it like this. You plot it like this, and then the sum should be over here, it should be equal to this. And there are a lot of naturally occurring phenomena. Okay, so it is sometimes better to come up with these distributions. So if you see this distribution, I came up with some random experiment, and then I'm saying, okay, this is what it follows. So in the world, or in so your day-to-day life, so there will be a lot of phenomena that will be occurring very frequently, and you can clearly see that there is a pattern to be followed. Let's suppose I'll tell you one thing. So there are a lot of experiments where you see success and failure. Okay, in your day-to-day life, you see a lot of phenomena where you see either a thing can fail or it can succeed, or there can be two values basically, either it can be 0 or it can be 1. You see a lot of phenomena of this sort. So what if we have a random variable for this, and we could learn about these distributions associated with those random variables, and we can make claims about these things. So that's where this concept becomes very important. Okay, let me take an example that was discussed in one of the blog posts, which was written in 2011 by John D. Cook. It's a very realistic example, and which you probably might encounter also. And then we'll introduce this Bernoulli and binomial random variables by this example. So let's suppose you are searching a website, you are seeing Amazon, you are seeing Flipkart or some other online website. So there you want to buy a product, okay, and you have multiple options there. You have multiple sellers for that product. So you want to buy a product, and you have multiple sellers. Now you know that for these multiple sellers, there is rating. There is a rating given to these sellers. Okay, this seller has this much rating. The product can be similar, or product can be different also. So now you have to buy a product. So for, let's suppose, one seller, so you have 94% positive reviews, but the reviews are 85193. These many reviews are given. And for other seller, you have 98% positive reviews out of 20785, and you have 99% positive reviews out of 840 reviews. Okay, this is the data that is given to you. Okay, this is the data given to you. Now you have to choose, so which buyer should I go with? So how many of you always are tussled with this problem? Whenever you buy something online, you somehow have to come to the decision, okay, I have multiple of these things, and by seeing this data, which should I choose? So now if you see here, over here is, so you are interested in what is the probability that you will have a positive experience. Okay, that is the probability. You will have to compute probability, because you have a product that you want to buy, and you have multiple sellers, and you have been given reviews out of these. Now you are tussled with the question, what is the probability that the positive I'll have the positive experience? This is somewhat probability of probabilities. Okay, I'll explain you how. So now consider this. So you basically have the probability. So you have to compute probability of positive experience given something. This is what you have to compute given some data. You have been given some data, and then you have to find what is the probability that I'll have my positive experience. Actually, what you have is, this is what you have to compute. This is what you are interested in. What you are given is this probability of data given the success rate. So let's consider this S. Let's consider a scenario like this. So you see there is this vendor, seller 1, seller 2, this vendor, and consider that they are selling something, and they are basically giving experience to people. Okay, better experience means, let's say, positive experience means positive experience, and they can give negative experiences. They can give two experiences, either positive experience or negative experiences. So if I am selling a product, I have a company. When I am selling a product, if my customer is happy, that means I am selling a positive experience. Otherwise, I am selling a negative experience. Okay, so if I count this, let's suppose, if I count this positive and negative experience, basically I am giving the data. Then I can compute, okay, this many times. So I'm having these things. I can compute probability of experience given the data, because I'm computing these things. Now we can simulate it probabilistically. We can simulate it. So if, let's suppose, somebody tells me that selling S, that S basically means success rate, or selling a positive experience is 0.95. If somebody tells me this, that this seller has this much probability, so now you have to compute probability that you will get a better experience. So it is like computing probability of probabilities. So you have this, you have S is equal to 0.95. That means having a good experience with this particular vendor is 0.95. So what is the probability that I'll have the better experience? So that means computing the probability of probabilities. Okay, how can we simulate this? Okay, now we have been given the success rate. So we have been given success rate, or we have been given the positive experience rate. So now, given that it is think it like a simulation, that now it is generating new data points. It is generating new data points. Okay, given this success rate, how can I come up with data basically? So I can simulate it. So how can I simulate it? Let's suppose I'll write a random program. So in the program, what I'll do is I'll say, let's suppose this is 0.95 is the success rate. I'll generate some numbers. So if I generate some numbers between 0 and 1, if I generate some random number between 0 and 1, I'll say any number that is generated, let's suppose that is below this, that means it's a positive experience. A number which is generated above this is a negative experience. Okay, so I'll randomly generate numbers. So this is like generating experiences when I'm having a customer. So now I know the prior, I know something about the vendor. Something about the vendor I know is that it has 95% success rate, or it has 95% of the times it will give me a positive experience. So if I want to randomly simulate now, so how can I do? I can either go customer by customer, have a customer and ask it, was your experience good? I give and the customer, was your experience good? And the customer, was your experience good? I can keep on asking them. In the computer, I can simulate this a little experiment. I can just randomly generate numbers between 0 to 1. If a number comes out to be less than 0.95 or equal to, I'll say this is a positive experience. If the number comes out to be, let's say, greater than 0.95, so I'll say it's a negative experience. Okay, it's a failure or success rate. How many of you are able to follow this? Because I have already been given success rate. Now I am trying to predict what is the probability that I'll have positive experience given this success. So given this success rate, what is my probability that I'll be having this positive? Let's pull up a little Python code and then simulate it. Give me a second. I'll set up. Let's do one thing now. So what we'll do is we'll try to simulate this situation, because let's suppose we already know that with this seller I have this much of success rate. Okay, let's call this as say some P number. Some P is success rate. So that is 0.95. Let's say this much. Oops. Okay, now what I have to simulate? I'll have to simulate for how many of people will have the positive experience. I'll see number of trials. Say I am giving a lot of people. Say I am giving number of trials. Say I am giving 50 people. So I am saying out of these 50 people, how many will get the positive review basically? Out of these 50 people, how many will get positive review? How many will get a negative review? I'll have to consider a distribution out of these. So now what I'll do is I'll have this much, and I'll say for, let's consider this, we'll make a list. Let's have customers, some CUS customers, and this is a list. Okay, in this list I'll put the positive customers, and then I'll also put the negative customers. Let's suppose I'll count them. So what I'll do is I'll generate a random number between 0 and 1. I'll compare that with this P. So if that number is less than, then I'll say this trial is successful. Otherwise, I'll say the trials are not successful. I can also compute the success. Let's do this. Let's append this. So I'll say, oops, for nothing in range of trials, number of trials. This is giving me everything. So I'll explain you this. So now you have this. So trial is equal to, so basically what I'm trying to do is I'm trying to compare. So I'll first have this numpy with me so that I can simulate this. So numpy as np. This trial is equal to, what I can say is np dot. So I have to generate a random number between 0 and 1, and I'll compare it with what? I'll compare this with the p, and if it is less than p, I'll say that this basically is success, otherwise it's a failure. So np dot random dot rand. Okay, so if this thing, so over here, give me a second. Let's consider this 1 and it's less than p. Okay, and then here over here I'll append this. So this, yes, these are the number of trials, and what I'll do is, so from this I'll say how many successes are there. So success is equal to np dot sum of trials. So I'll say success is equal to np trial dot sum basically, and then I'll say append that to the customers, append that to customers of these success. So I'll get this. Okay, so this is what I wrote over here. So I just need to test it if it is working right, because I'm not sure. Just need to check it first. Yes, it is working. So I think if I print customers, let's suppose I want to see customers. What is this? How many reviews are there? 50. Yes. So if you see, this is working right now. So this 1 basically means success and 0 means failure, or 1 means positive experience and 0 means negative experience. So if I am running this for 50 people, okay, if I am running this for 50 people with the probability, with the success rate of this much, with a success rate of 0.95, I want to see my customers. I want to see for how many customers did I got positive experience and how many customers I got a negative experience. So if you see over here, you see for all of these 50 I got a better experience, okay, for all the 50. And if I again print it, now you see for 1 and 2 and 3 and 4 people, for 4 people I got a bad experience. If I again run it, for how many people? For just 1. So you see now this, when I'm simulating it, so you can see something of this sort. So I'll just write it over here. So out of these n trials, so I'm performing n trials. When I perform this n trial, so what is happening now? So the possibility, I have total 50 people. So I have total of 50 people. So now I'll get all the combinations. Either I can get 50 failures and 0 good reviews, or I can get 49 failures and 1 good review, and keep on going, I'll get 50 good reviews. So all of this is possible. So isn't it possible? Because it's a probabilistic process. So how many of you are understanding till now? Okay, I will go back to code, but before that we will have to understand this. So I had 50 people. So the possible things are, I'll have 50 bad experiences, 0 good experiences, or I'll have 49 bad experiences, 1 good experience, till 50 good experiences and 0 bad experiences. So all of this is possible. All of this is possible. But you know that the success rate is 0.95. So this is extremely unlikely. So all the 50 reviews will be bad is extremely unlikely. If I send all the 50 customers to this, so because I know the success rate is 0.95 or the good experience rate is 0.95, so this is extremely unlikely. Okay, then what is more likely? So is this more likely? So how much likely is each of this among these? How much likely is each of the outcome? Consider this as each of the outcome. So how much likely? Don't you think it will come out to be a distribution of some sort? So here you can consider distribution. So let's suppose this will be 0 good experiences, 1 good experience, 2, 3, 4, till let's suppose 50 good experiences. This will come out to be a distribution, and this distribution will somehow look like this. Somehow, I'm just giving you a vague idea. So here, let's suppose if I keep on performing this experiment, if I just keep and count, so I can do also that. If I keep on if I keep on counting these things, and you will come up with some distribution. So distribution will be of some this sort. So if you see that more of the review, let's suppose this 50 is also extremely, this is not extremely unlikely in this case because 0.95 it will be likely. So but this is extremely unlikely, so maybe it will be skewed like this, it will be a bit skewed like this. Okay, these things are extremely unlikely. Why? Given the 0.95. So even if you change the 0.95, then what will happen is distribution will be shifted. So how many of you are following the discussion? So again, I'll summarize the discussion. So we had some probability of success. The probability of success was 0.95. So I want to simulate. So now if let's suppose I am having I'm giving customers to that vendor. So what is the probability of success rate? So I am trying to simulate that. So I am saying you that these are the possible things. So in 50 customers, so these are the possibilities that they'll have either positive experience or a negative experience based on this. And from that we can come up with a distribution. Okay, distribution will be like this. All of these are positive experiences. Okay, and here we can say percentage of the people. Okay, something of this sort. So now while simulating, I was showing you the same thing over here. Again, coming back to the code, that's what I was showing you over here. So I was showing in the code that I just had this P as success rate. I said number of trials is 50. That is, I have 50 people that is going to that vendor. So I'm saying out of these trials, so I am generating a number between 0 and 0.95. So if that number is less than 0.95, that means a success. Otherwise, it's a failure. Okay, so that is how I am appending these customers over here. So you can see either 0 is getting appended or 1 is getting appended over here. Okay, so if I keep a track, let's suppose if I perform this experiment continuously, you will see that this comes out with a probability distribution. Okay, so I have written a piece of code that will show it over here. I'll plot this also. So if you see, I'll just plot it without showing you the code. I'll plot these things. So you can see the plot over here. Don't get scared because all of this thing you know. So here you see the distribution over here. The same thing is number of success. I have 20 trials now. Okay, the success rate, I think I have given some number. So success rate is 0.3. Okay, I could have chose 0.9 also. So here success rate is 0.3 and the number of trials that I did is 20. So now I can have 20 positive experiences, but only success rate is 0.3. That means this is very extremely unlikely. This 20 over here, if you see this over here, this is extremely unlikely, this case. Why? Because my success rate is 0.3. Okay, how many trials I am doing? I'm having 20 customers now. So you see a distribution. 0 is also extremely unlikely, but there is a possible that out of these 20, only some percentage will this. Okay, and then I'll have also some people. Let's suppose this is 0, this is 1, this is 2, and this is 3. If you clearly see that, so if you see the peak of this is over here. Peak of this is over here. So here, if this is the peak, somewhat around 6. So if you see 6 by 20, that should come out to be 0.3. So that is what the success rate means. So probability we have success rate of 0.3. So we are expecting this sort of distribution. But I now plotted all the distributions over here. So this distribution was plotted by the simulation. All of these things were plotted by the simulation. And this is what was created by the formula. So how many of you understood this? I know that you can write the code. So I just pasted some lines of code over here, which I am not showing. This is pretty easy to count. So I just wrote the code for the simulations. And this matplotlib code, you can easily understand it, because we have done enough matplotlib. Yes. So if you again here, if you now see it over here, if you see in the code, so what we have, the thing that we had is over here was probability of success. We'll say that P, that probability was given as 0.3, let's suppose. Okay. And how many trials were performed? That is number of N was performed 20. So consider it like this. So a vendor was selected, which was assumed to have success rate of 0.3. That is giving positive experience 0.3 times. So I wanted to see for how many people will it give positive. I want to simulate the condition. So simulation could be possible. It will give 0. So here this is number of successes. That means the people who had the positive experience. So because it has only probability of 0.3. So this thing is extremely unlikely. That is all the 20 people will have good experiences. And even this is also extremely unlikely. 15 is also unlikely. So you can see the 0 is also unlikely, because at least 0.3 is some decent probability. So if you now see over here, so the peak that you see comes around to be around 5, 6, 7, something like that. So that justifies this probability. But you can still say that even with this probability, you cannot come with just number. If I perform the experiment, let's suppose for 20 people, all the 20 people, or maybe let's suppose 720 people, but you are saying that it is very highly likely that 7 among them will fall into this. That's why you are repeating the experiment. If I change this probability, you will see the distribution getting changed. If I change this P, let's suppose, I'll see where this P is. So if number of trials that are happening is here 1000, so I'll just change these things. So this is 20, so I'll change the probability of success. I'll change it to probability of 9.5. Okay, and then I'll see the graph for not just 20 people. Let's suppose we'll have 50 people. Now you see the graph over here. Okay, the distribution gets skewed, so it is very unlikely. So in this case, in this particular case now, the probability over here is 0.95. So I am saying for 50 people. So N is equal to 50. That is, if we are given that 95% is the success rate, 95% of the times that this vendor is giving positive experiences. So for how many people? For how many people will it give success if I run it for 50 people? So you can see that it's very unlikely that all the people will get bad experience. 0 is very unlikely. So that's why you see a tail distribution over here. You see from 0 to 40, almost this is very unlikely that 40 people will get bad experience or 10 people will get. So how many people will get good experiences is always above than 40. You can see over here. Okay. So what is very highly likely? So highly likely is around over here. So you can see this. Around 48 people will get good experience and 2 will get bad experience. Okay, so this depends on what is the success rate of this. Okay, but it still is a probability distribution. You cannot say that this is not going to happen. Let's suppose we can have 46 good reviews and 4 bad reviews. Okay, this is also a possibility, but how much possible this is? That's why I said it's a probability of probabilities. So initially we had this probability of success. Then I am saying that probability will have good experience given this probability, given this success rate. Okay, so this is where this probability distribution of these random, these Bernoulli and this binomial random variables come in the picture. So this in mathematics is known as this thing over here is known as binomial distribution. Okay, this is called as binomial distribution. The thing that you saw over here. Now we'll see. This is what we achieved by using simulations. Okay, this is what we achieved by simulation. Now we'll derive it mathematically, and I'll show you that mathematical notion is much more cleaner than the simulation, and you can just think mathematically because till now you have been trained to think mathematically rather than the simulation. But the simulation is the right approach of thinking in the real world. You can perform the simulations, but when you are having these mathematics too, you should be able to compute this. Just keep this at the back of your head. And now we'll formally define what a binomial and what a Bernoulli random variable is. The first thing that we'll define is Bernoulli random variable. So Bernoulli random variable. I hate the names. I hate to remember the names. I want you to remember the concept and learn the concept rather than just going with the name. So there was this guy, James, I think Bernoulli, he discovered this concept. So this Bernoulli random variable, it models an outcome for a single trial of an experiment, where as I said, either it can be a failure or a success, a failure or success. Okay, and let's suppose I can write it like this: Bernoulli. It usually written like this: Bernoulli of P. So this P is what the probability of success. P is defined as probability of success. Okay, this P is defined like this. So Bernoulli random variable basically models an experiment where you have these trials and the outcome possible is 0 or 1, that is failure or success. So what is the PMF of this? So probability mass function goes like this. So probability of success, that is probability x will take value 1 success is equal to P, and probability x will take value 0, that is failure, is 1 minus P. This is its probability mass function. Probability mass function of Bernoulli random variable. Okay, so this should be between, this P should be between 0 and 1 to respect the axioms of probability. Okay, and this is the probability mass function of this. And let's suppose we have flip of coin. So if I say suppose you have a fair coin and you flip it, if head is a success and tail is a failure, so you can say we have success probability 0.5. let's say it's a fair coin, so 1 minus P is also 0.5, that is success is 0.5 and failure is 0.5. Okay, so now if I define, let's suppose some problem. Okay, what is the probability that I'll get 10 successes? I'll get 10 successes in here. Okay, if I flip the coin, let's suppose 20 times, something of this sort. This over here, this experiment is modeled, this is modeled as Bernoulli random variable. Okay, and it also in the defective product, let's suppose when you have a factory in that you test these items, the probability that the item will be defective is, let's suppose, 0.1. This is failure probability. Okay, so we have again, so this P is equal to 0.9, that is success, you will have a good product, and Q is equal to 0.1, you will have failure, you will have a product that is defective. This is how you model these things. Now why does this binomial random variable come into the picture? So binomial random variable comes in the picture when you have repeated trials of these Bernoulli random variable. So a binomial random variable extends the Bernoulli random variable concept. Why? Because you have now repeated things of this. So one experience, when you were going to this website to purchase a product, you can either have a good experience or a bad experience. So that is either failure or a success. Good experience is success and bad experience is failure. Now you have this, you can model that as a Bernoulli random variable. So why this the binomial random variable comes in the picture is that if you repeatedly perform, if you have multiple customers, if you have 10, 20, 100, 200 customers, that means 200 people are going to this where you are simulating this problem. So now in binomial random variable, you have two things. One is probability of success, okay, and then the second thing is number of trials. How many trials are you performing? So I said binomial random variable, it extends the Bernoulli random variable. So it extends the concept of Bernoulli random variable to n trials. So Bernoulli was restricted to one trial. If you just perform one trial, you have probability of success, you have probability of failure. That is, if you have a random variable, you have been given corresponding PMF of that. That is final for that. But now once you go to binomial, so binomial extends one step ahead. It says if you now have n trials, all the individual trials, or Bernoulli, all these n trials, each trial is a Bernoulli random variable. Okay, that means the possibility is success or failure. The possible success or failure. So you can either fail or success, and then you have been given this probability of P. So these two things are called parameters. So this n and P are called as parameters. Okay. Now suppose if let's suppose you might have heard this x is sampled from binomial random distribution with n trials, and let's suppose P probability success. This is how it is written usually. If you see even machine learning research papers, or if you see, let's suppose, any type of mathematics book, that is how this thing over here says it is sampled from. So we have x might be a sample. So this is sampled from the distribution, that is binomial distribution, and it has n trials are performed and P is the success rate. Okay. Now how to basically consider the PMF of this? So if you have a random variable, so for that we require a PMF. So then we'll say the random variable is complete, because random variable is a function which maps input to the real value, to the sample space, to the real value. Now for that you will have to give a PMF for this. You have to give PMF for this. So now if you are given this n and p parameters, you are given that, okay, what is the probability that this x will take k value? Let's suppose probability that out of these n trials, probability out of n trials, k will be successful. Okay, so this is what you have to compute. Basically, if you have a variable x which follows this binomial distribution, so you will say that probability x will take k value. What is the probability of this? So now you have to get k success. You can take an example. Let's suppose 1 is success and 0 is failure. I have to take k ones and rest are the zeros. So this should be p to the power k, because success to the power k, and all of these things are independent, multiplied by 1 minus p. 1 minus p is the failure, and minus k, because total times we are performing n experiments. But you know that how many times will this be done? So this will be nck. Okay, so this is my success, this is my failure over here, and this is my total number of possibilities of that. Okay, and this over here is PMF of binomial random variable. Okay, this thing over here. By now you should be experts in this because we have done a lot of combination permutations. So P of k means probability of success for k of these events are successful, multiplied by 1 minus p, that is failure for n minus k, and how many possible are there. So it is like this: you have k of these ones, and then you have followed by k of the zeros. Let's say n minus k of zeros. Now you can permute them in different you can permute them in different ways so that you get these number of combinations over here. Okay, so this is the possibility that we have, or this is the PM of random variable. Now the question that we had been given like this. So the experiment we did is we have been given p is equal to 0.95. that was given to us. The success rate is 0.95, and we had trials, n is equal to 50. So we are performing the trial on 50 people. So we are performing this trial on 50 people. So what is this? What is probability that this x is actually derived from this? The x is derived from binomial distribution. Binomial distribution has n 50 and p is equal to 0.95. So now you can, and if we want, let's suppose this, if we want to compute 48 success and 2 failures, okay, that we saw graphically as well. So this will be equal to 0.95, that's the success rate, 0.95 to the power 48, and 0.05 to the power 2, and how many of these? So 50 out of 48 successes we want. So you can compute the probability directly, or you can see it graphically that we saw in the code window as well. So that code in the code window we saw this. So this, if you see, so this over here, it is giving you also the probability. So over here you can see this is giving you probability of percentage. So probability is here. So you can see, you can compute this either by simulations, or you can compute this by directly using the binomial probability. So if you see this red curve, so this red is theoretical combination. The formula over here, the theoretical is nck p to the power k 1 minus p to the power n minus k. This is what this red thing is. Okay, so you can see them overlapping, and this over here, this blue over here is by simulation. And now I'm in a position to explain you the code. So but you saw that the simulations as well as the formula of binomial random variable give the same answers. Is it clear so far? Is it clear? Okay, so we had two things now. We can either simulate it or we can use the mathematics. So I said usually you will simulate when you have some real world experience, so you have to simulate it. But if you have mathematical tools under your belt, so you can just pull up that tool and then you can compute the probability, and simulation should agree with the mathematical formulation or with the theoretical PMF. So the PMF we had over here is this. So this blue over here is the PMF, is the simulated one. So when we simulate the condition, and this red over here is the theoretical one. So you saw that theoretical and the simulation is giving almost the similar results. Okay, now let's look at the code and how do we got it. Give me a second, I'll explain you people the code. The first thing is to simulate the binomial, and with this is n is equal to a number of the things into consideration. In this case we had 50 and 8, or you can say p is success rate, and number of trials, basically how many times do you want to repeat the experiment. The method one was using the binomial function. So this is directly binomial function. So in NumPy we have a binomial function that basically uses the formulation that I just showed you, nck p to the power k and 1 minus p n minus k. This is the formula that it uses. And method 2 is by using the simulation. So this is the method 2 which uses simulations, and it returns the both results. It returns this results from NumPy and results from simulations, results manual. Okay, now I am plotting these things over here. Plotting is pretty easy. Okay, so this is my x-axis and this is my PMF. for binomial, and I'm plotting this thing. So over here, this is all plot the figure, plot the histograms over here. Okay, and I don't think we require this mean and stuff, so this can be removed from here. And now if you see n is equal 50 is this is number of trials, and then we have p is equal 0.95, this is success rate, and then this is actual number of trials, how many times do you want to repeat the experiment so that you get this result. So you have to repeat the experiment these many number of times, let's say 10,000 number of times. So I'll run this simulation. Okay, so one result will give me the simulation from the actual simulation, and the second result, this is the actual simulation, and this is the result from the formula, theoretical answer. So now I'll plot both of these things. I'll plot the binomial distribution using the NumPy. I'll plot the binomial result using the manual simulation, and then I'm printing these results. So this can be seen, and these are the two plots that we get. Okay, so one plot is over here, this blue plot is simulated, and this red plot is theoretical plot. Okay, and this was simulation with you can check it with different numbers as well. Okay, this was a binomial distribution of these things. Any questions still here? So we saw a couple of things today. So we saw what a random variable is. We saw that random variable is not a new concept, rather it is a new perspective that will apply on the concepts that we have learned. And then we saw that it's a function which maps the outcome or the sample space to a real number. Okay, and then we saw there is a possible distribution. So what is the distribution? Some phenomena occur in a real world which are repeating. So there is a repeating pattern. So let's suppose in a lot of problems you can see failure and success. You can see that in coin tosses. You can see that in reviews. You can see that in, let's suppose, defect items being defective or being good. So you can see this pattern of failure and success all over. So what mathematicians have done is, okay, let's come with a random variable which will try to model that problem. So that the first thing that we saw in that was Bernoulli random variable. So Bernoulli random variable is a random variable which takes two values. It takes either success or failure, and there is a probability associated with success. So with each random variable there is associated probability mass function. Okay, so we define the probability mass function for Bernoulli random variable, and then we said, okay, let's extend this thing to the binomial random variable. So now if you perform this repeated experiments of these failure and successes, so you get what's called as binomial random variable. So we constructed also a PMF of that. We saw a simulation for that, and we also saw the theoretical foundation theoretical PMF for that. Okay, so binomial random variable has two parameters. One is number of trials, and p is the probability of success. Now if I put n is equal to 1, so then it becomes Bernoulli random variable, because n is equal to 1, this is with p. Okay, so now if you have repeated trials of binomial random variable, this Bernoulli random variable, you will come up with binomial random variable. Okay, why is this called binomial? Because you saw that we got a coefficient over here. So this over here is from binomial theorem. Okay, these are called as binomial coefficients.